Galvanic cells. What is a galvanic cell? Well, we already talked about redox reactions, and a galvanic cell is a place where these redox reactions occur, or in this case defined as a device in which chemical energy is changed to electrical energy. So let's look at an example of one in a minute. A galvanic cell uses spontaneous redox reaction to produce a current that can be used to do work. The key here is spontaneous redox reaction. That would of course mean one where delta G is negative. So if delta G is negative, we can use a galvanic cell to see what the reaction is. Think of an earlier reaction we did where we had 8 hydrogens and MnO4 negative and 5 irons producing Mn plus 2 plus 5 Fe plus 3 plus 4 waters. And I think we balanced this one using the method of half reaction. And of course, when we have the MnO4 negative ion and the Fe plus 2 ions present in the same solution, these particular substances will transfer electrons immediately upon their collisions. Remember, thinking of the collision theory, which we'll get to, reactants have to collide to form products. So once this is in solution, the reaction happens immediately. But because they're transferred directly when they collide, no useful work is obtained from this chemical energy that's involved. Instead, it's released as heat. So what a galvanic cell does is it harnesses that energy to do useful work, like move a wheel. And of course, moving a wheel can make electrons move, and we could eventually, with enough energy, turn on a light and make a light bulb turn on, etc. So a galvanic cell is harnessing spontaneous redox reactions to do useful work. So what would one look like? Well, here's an example of one. This one shows what they're doing is they're actually separating the two reactions into two sides, so that instead of the reaction happening immediately in one container, the electron flow can be harnessed. And you can see here, this is the electron flow. So what are the parts of a galvanic cell? Well, you have in this case, 2 beakers. One is the anode, and one is where the cathode. The anode is where oxidation occurs. And a cathode is where reduction occurs. This is how you can remember it. Anox, red cat. In other words, if you saw a large animal called an ox, this is the first one, you could say, hey, I just saw an ox. So anode is oxidation. Red cat, obviously another animal, a cat that happens to be red. It's pretty odd. Red cat, reduction at the cathode. So anox and red cat help us remember which is happening in which compartment. So on the left here, and normally we put the anode on the left of the picture. So the anode is where oxidation occurs, and that's why you can see it says reducing agent. There is a porous disc here, almost like a semi-permeable membrane, or there can be what's called a salt bridge. That's what we will be using, and that's kind of a U-shaped tube. That's not very good. It's a poor drawing, but you get the idea. There's a salt bridge in here filled with a chemical that allows the electrons to continue to flow. But I'm going to erase it because you don't need a porous disc and a salt bridge. But you can find, I'm sure there are pictures in the textbook of a salt bridge and a porous disc. In any case, the reaction always moves from anode to cathode. Because remember, oxidation is losing electrons. So if this one loses electrons, it can give it to something that would like to gain electrons, which is being reduced. Usually what happens is we have some sort of a liquid in here, and the liquid is some sort of a salt that contains a metal ion. And it's specific to that particular situation. So for example, what would be an example of a kind of metal? Well, we might have zinc, a piece of zinc, solid zinc, and some zinc sulfate, ZnSO4. And on this side, we might have some other kind of metal, something else. So that metal, whatever it would be, and it's metal and SO4 with a plus in solution. So the metal and the salt of that metal is in the same side of that particular compartment. Could be copper, it could be silver, gold. We don't have enough funds in the science department to do any experiments with those kinds of metals, but you get the idea. So what happens is, during the process of oxidation reduction, this electron can flow, and we can do useful work. In other words, we could, usually you will see like a voltmeter up here, and it can register how much voltage is passing through. Remember, oxidation occurs at the anode and reduction occurs at the cathode. And the salt bridge or the porous disk allows the ions to flow without extensive mixing of the two solutions, and that allows us to do useful work. The salt bridge contains a strong electrolyte held in a jello-like matrix, so it's kind of a thick chemical, usually potassium nitrate, that allows electrons to flow. The porous disk, however, contains tiny passages that allow this flow of ions. A galvanic cell consists of an oxidizing agent in one compartment that pulls electrons through a wire from a reducing agent in the other compartment. It's really the difference in those potentials that cause the electrons to flow. The pull, or the driving force on the electron, is called the cell potential, or E cell, or sometimes it's called electromotive force, or EMF. You see this fancy looking E, this fancified E. That's how I draw it, but I think on the cheat sheet they have now actually gone to just a plain old boring capital E. So notice this tends to be what the book will use, this fancy E, and I will use it, but I think your cheat sheet uses just plain old E. So this pull or driving force, the cell potential, is the energy that is harnessed as a result of the difference in the two substances. The unit of electrical potential is the volt, and probably back in physics, when you talked about electricity, you talked about voltage. 1 joule of work per coulomb of charge is transferred. That's what a volt is, a joule per coulomb. So that's the kind of units we will be using a little bit later.